All right, my name is Miss Lamens. If you haven't met me, I am the other chemistry teacher, one of the chemistry teachers here. So we're going to be doing waves and light. Now, you should have watched an Edpuzzle last night, so you should be pretty familiar with at least the basic terminology of waves. And you should also have a worksheet that goes along with this PowerPoint / video. Feel free to pause the video at any time so that you can make sure you're staying up to date with the paper. Some of the things on that worksheet are going to relate directly to this PowerPoint and this conversation, and some of them are just going to be kind of independent on that worksheet alone, okay? Okay, so today we're going to be talking about how the movement of electrons can impact the energy of an atom. And we were told in the video last night that waves are characterized by three things: frequency, their wavelength, and their energy. Now in the video, they talk about speed, but speed is synonymous or the same as energy. So the anatomy of wave, the crest is this tippy top portion here. The trough is this very bottom portion here. One wavelength is from crest to crest, or trough to trough, or from equilibrium to the next equilibrium. So that contains one trough and one full crest. An amplitude is from equilibrium, which is the center of the wave, to the top or equilibrium, the crest, or equilibrium to the trough. And the frequency is just how many of these waves happen in a certain period of time. If you think about it, how frequently something happens, if something is more frequent, then it's going to happen more often. If it's less frequent, then it's going to happen less often. Okay. I think that's it. Okay. So the types of waves that we are talking about, in the video they mentioned they were called transverse waves. These waves are also an example of light waves. They are based on the electromagnetic spectrum. Okay, so you can see if you read the types of waves that are in this electromagnetic spectrum. We have gamma rays, X-rays, ultraviolet, infrared, microwaves. This is my favorite because it prepares all my dinners, and radio waves. Okay, so we have all of these different types of waves, but I think the one we are most familiar with is visible light. It's because of the visible light waves that we're able to perceive everything that we see, everything. Any color that you see or lack of color, if you're colorblind, any of that is due to visible waves. So as we look at this table or this diagram rather, you should take note of the things that are labeled. We have energy here, wavelength here, and then frequency on the bottom. So if you see this arrow, as energy increases as we go from right to left, okay? As we go from right to left, you can also see that the wavelength decreases. We have very long wavelength from crest to crest versus a very short wavelength from crest to crest. As we go from right to left, the frequency also increases. You can see here that waves are happening more frequently over here, and waves are happening less frequently over here. So as I said before, as wavelength increases, frequency decreases, and we can see that by looking at this table. If you're going to be squeezing a bunch of waves into a small area, those waves are happening more frequently, but the waves have to be shorter. All right. This is called an inverse proportion. So as one value goes up, the other goes down. For instance, as wavelength increases, frequency decreases. The other one we've talked about is a direct proportion. So as energy increases, frequency increases. Okay, down here. This is a direct proportion, so that means that if one goes up, like energy increasing, the other also goes up, so frequency increases. So like I said before, frequency is the number of waves that pass through a point in a given time, and we measure it in hertz. So if you look at these two waves below, I have one, two wavelengths, and down here I have 1, 2, 4 wavelengths. So if we have a smaller frequency, so this is a smaller frequency because it's happening less frequently, we have a larger wavelength. We can see this. This is a much larger wave than this. This seems a little squished. So applying our knowledge of a direct proportion, we have a large frequency. That means the other thing is also going to go up. So we also have a large energy. So feel free to pause the video at any time to kind of catch up on notes. Okay, so this is a little confusing because our electromagnetic spectrum is just kind of flipped from where it was. Over here we have like a small wavelength versus very large wavelength. So it's the other way around, but we could still use this infographic to kind of help us understand wavelength and frequency. So right now we're kind of zoomed in on the visible spectrum. You can see it's a very small sliver of this entire electromagnetic spectrum. Violet has the smallest wavelength, okay? Which means if it has the smallest wavelength, it occurs more frequently. So it has the largest frequency in the visible spectrum, and it has the largest energy. Whereas red is the opposite. 700 nanometers is a lot larger than 380 nanometers, even though nanometers is kind of a small measurement itself. And just keep in mind that we do measure wavelength in meters. So you want to really brush up on your conversions. How many nanometers are there in 1 meter? Okay. All right, so the inverse relationship between wavelength and frequency can be described with this formula. All right, you're only going to need to know 2 formulas, 2 equations for this exam. So this one is broken down into F for frequency, which is measured in hertz. This is called lambda for wavelength, and it's measured in meters. And then this is C, which is the speed of light in a vacuum, and it's a constant. So a constant means that it's a number that you will always use. It's always given to you. It's just like Avogadro's number in that it will always be 6.022 times 10 to the 23rd. But in this case, we are using the value 3 times 10 to the 8th meters per second. Okay, so that is something that will be given to you on your test. You shouldn't have to memorize that constant, but just realize that it's given to you. Super secret tip. If you have a problem on your test or in your practice problems that says anything about wavelength, you're going to use this formula. If it mentions it as something you need to solve for, or if they give it to you, you need to use this formula because it's the only one that has wavelength in it. So if we wanted to describe the direct relationship between frequency and energy, meaning that they both increase together, we're going to use this formula. Frequency is measured in hertz, that's the letter F. Energy is the capital E, and that's measured in joules, capital J. And then again, we have another constant here, which means this is a number that's given to you. You don't have to memorize it. And it's used just like the speed of light in a vacuum or Avogadro's number. We use that constantly. And this is Planck's constant, and it is 6.626 times 10 to the negative 34th joule seconds. So again, another secret tip is that if you have a problem or a question that has anything to do with energy, you're going to use this formula because it's the only one that has energy in it. Okay, so in this class, we're going to be using the guess method. My students are familiar with this. Ms. Bakeman's students might not be familiar with this yet, so I'm going to do my best to teach it to you. GUESS, G-U-E-S-S, is an acronym that we use to set up math problems. G is for given, U is for unknown, E, equation, S, substitute, and the other S, solve. I'd like you to take a minute to pause the video to go ahead and read through each of these red points. Okay, so let's apply the guess method. We know that given is whatever we're given in the form or in the question. So it says here, a wave has a frequency of 6.35 times 10 to the 5th hertz. Calculate